Okay, in this video, I want to talk about how to solve something called related rates problem. So you can think of, rates should be a common idea now in calculus. A rate is, or a rate of change, is basically the derivative that we've been working with. This is looking at how two rates in a certain situation, like a real-world situation, might be related, and how we can solve for one rate using another rate. So this is basically an application of the idea of the derivative to real-world problems. And I think the easiest way to teach this material and to learn it is just to see some example problems, and I will kind of point out along the way some general ideas or approaches to these sort of problems that will help you to solve different types of related rate problems. So I'm going to go through 4 examples in this video and kind of point out ways that you could kind of apply a general problem solving approach to these sorts of problems. Alright, so let's just start with the first problem. It says a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So there's the information. I think that in general, what we want to do is we want to start off, if we can, trying to draw a picture of what's going on, and then label it, and then figure out what we know and what we need to find. All right, so I'll even kind of put that on a separate piece of paper here. So let's just kind of start off with one. I want to draw a picture, if I can, of the situation. It doesn't have to be a great picture, it just has to be something that I can look at to help me think about what's going on in the situation. Secondly, I want to label it. I want to label the picture. Usually we're going to include some symbols, things that we can use that we can put into an equation so that we can use some of the mathematics that we know or that we are using in terms of derivatives to solve the problem. We want to identify what we know, or the knowns. What are we given to work with? And then fourth, what do we need to find? What do we have to solve for in the problem? It's important to kind of know, kind of like getting in a car. You don't just get in a car and start driving around. You know where you're headed. So after we have a picture, which kind of supports our thinking about it, we label it, we identify the knowns in terms of some of those labels. We need to know where we're headed. What do we need to find? Because ultimately, when we go back and look at what we've done here, we need to think about it in terms of ultimately what's the goal of the problem. So going back to the original problem then that we had, let's start with drawing a picture. All right, so here's a wall, here's the floor, here's a ladder. All right, so there's a picture. Again, nothing spectacular, but it gives us something to label and supports our thinking about the problem. So we know that the ladder is 10 feet long, so I'm going to label that with 10. What are some other quantities that we need to label? So as the bottom of the ladder slides away from the wall at a rate of 1 foot per second, so that's this distance here, and it's changing at 1 foot per second. How fast is the top of the ladder? How fast is the top of the ladder sliding down when the bottom of the ladder is 6 feet from the wall? So we have a couple things. We have this distance right here from the wall to the bottom of the ladder. I'm just going to call that x. And then this distance here from the floor to the top of the ladder, I'm going to call that y. Simply just to use the convention, you can kind of think of this as, we're in the xy plane here, right? And this gives us a way to think about vertical distance and horizontal distance. And an important idea here is that anything that is changing in the problem, for example, it says when the bottom of the ladder is sliding away from the wall. So this distance is changing, and we want to find out how the top of the ladder, how fast is this sliding. So this is changing also. We want to label those with variables, not with constants. All right. Constants are reserved for things that don't change in the problem. As this ladder slides down the wall, it doesn't change its length. But this distance and this distance will change. Okay, so what else do we know? Well, we know that it's when the bottom of the ladder is 6 feet from the wall. So we know that x equals 6 right at this particular point in time. What about this right here, this rate? Well, when we see rate, think derivative. And what derivative are we talking about? We're looking at, so it's feet per second, so it's a distance with respect to time. And it's the bottom of the ladder sliding away from the wall. So it's how this is moving this way. So that is dx dt. In other words, it's how the horizontal distance is changing. The x represents the horizontal distance. How the horizontal distance is changing with respect to time. All right. What else do we know? Do we know why? Well, they don't tell us why, but we should be able to solve. We'll talk about that in a moment. And then what do we need to find? All right, it says how fast is the top of the ladder sliding down the wall? So in other words, how is this distance changing? This vertical distance? That would be dy dt. Okay, so that's what we're after. We want dy dt. So let's start off here with how do we relate all this? So these distances to each other, and then how do we relate the rates to each other? So we can assume, although you'd be surprised, that the wall and the floor are at 90 degrees. In reality, that actually does not usually work out. If you've built houses, you know that. But we can assume, for the sake of this problem, that it's close enough to 90. We'll call it 90 degrees. And because of that, then we can use the Pythagorean theorem to relate these things to each other. So I know that x squared plus y squared equals 10 squared. Initially, I want to keep these in terms of variables. I'm only going to plug in if I'm trying to solve for something. So notice then, if I know that x is 6, the hypotenuse is 10, I can solve for y, right? And we will need that down the road. So let's put that in. So I'm going to have 6 squared plus y squared equals 10 squared. All right. So y squared, that's 36, that's 100. Subtract 36 from both sides. I get y squared equals 64. Which means that y equals 8. Y equals -8 will also satisfy this equation, but it doesn't make sense in terms of our problem here because we want a positive distance here. All right, so we know y equals 8. Now, how are we going to find dy dt, and how is it related to dx dt? Well, ultimately, we can take the derivative of each of these terms with respect to time. And this is where the chain rule comes in. I will just explain this once and just kind of use it for the rest of the example problems I'm going to go through. But we can think of, for example, x as some function of time. It just means that x changes as time changes. So over time, this vertical or this horizontal distance is changing. Now, what I have here is an x squared. So if this is squared, then we can think of this f of t as being squared. All right. Now, by the chain rule, if I want to take the derivative of this, the outside function is x squared, right? So if I took the derivative over here, I'd have 2x, and then over here I'd have 2 times f of t, right? Since x equals f, 2x. Now, by the chain rule then, because this is a function that's being squared, then we also have to multiply by the derivative of the inside function, or times f prime of t. That's the chain rule. So the first part is just our 2x that we get from the power rule, but then we have to multiply by the derivative of the inside function. So I'm not going to change everything to this notation because it gets a bit cumbersome, but I think it's important to note that it is related to the chain rule. And so here, instead of calling it f prime of t, we're just going to call it dx dt. All right, so those are equivalent. But this is just to show you, because it might not be apparent if I just wrote down. So if I take the derivative, I'm going to take the derivative of this with respect to t, and take the derivative of that with respect to t, and take the derivative of that with respect to t. So coming down here then, I'm going to end up with 2x dx dt plus 2y dy dt. And then the length of the ladder is not changing with respect to time. It's constant. So that's going to be 0. Another way to think of that is when we take the derivative of a constant, it's 0 because there is no change. There's no rate of change. Okay, so, but where would this 2x dx dt and 2y dy dt come from? They come from the chain rule. All right, so we're going to see that again and again in these problems. All right, and then this gives us a way to relate. We needed a way to relate these rates. That's why these are called related rates problem. Well, the question is, now we know what x and y are, right? We know that x is 6, and we found y to be 8, so I can say that's 8. So I've got 2 times x was 6. Now dx dt, do we know dx dt? Well, That's what this is right here, right? It's telling us that the ladder slides away from the wall at a rate of 1 foot per second. So dx dt is 1 plus 2 times y, which we said was 8, and then times dy dt. That's what we're looking for, and the whole thing altogether equals 0. So this is where we see we're going to be able to solve for dy dt now because we know everything else. One other thing I should point out here. So notice that I took the derivative first, so I ended up with an x and a dx dt and a y and dy dt. Only then do I plug in these values, because remember, these are changing in the situation. We are looking at one particular point in time. So first we need to get this expression, then we plug in the 6 and the 1 and the 8, because we're looking at this one snapshot as this ladder slides down the wall. All right, now at this point, I'm going to just go ahead and solve for dy dt. So that's 12. I'm going to subtract that from both sides, and this is 16. So I have 16 dy dt. If I subtract 12 from both sides, that equals negative 12. And then divide by 16. So dy dt equals, and I can simplify that to negative 3/4, and that's feet per second. Now notice, in terms of our situation, that makes sense because the top of the ladder is sliding down, which is in the negative y direction. All right. This also shows, I think it's a common misconception that the rate at which this goes out and the rate at which this goes down are always the same. They're only the same if y equals x, right? If they were like both 6 or both 8, although that would change our hypotenuse. But the point is, if they're exactly the same, then they would be moving at the same rate. Otherwise, if this is higher up, it moves more slowly at first, and as it gets closer to the bottom, it speeds up. All right. So likewise, this was going faster over here and slowing down as it gets farther away. So, anyways, this makes sense in terms of the situation because this y is we're going in the negative direction. Y is getting smaller, so it's decreasing at 3/4 of a foot per second, or we can just say it's changing at negative 3/4 of a foot per second. Okay, that is the first example. Let's look at the second example then. I've got air being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. And the question is, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? So if we go back to our little list of what to do and in what order, first I'm going to draw a picture, and then I want to label the picture, identify what we know, and then identify what we need to find in the situation. Okay, so I'm going to try to draw this spherical balloon. All right, so we'll start with the circle. You can kind of think of, this is kind of the back side of it, and the front side, trying to make it look somewhat three-dimensional here. But the important thing is not how good your picture is, it's whether or not you can use it to kind of think about what's going on in the situation. So here's my balloon. Let's go back to, what do we know? Well, we know that volume is increasing. All right. So you may or may not know this. You could always look it up. But the volume of the sphere is 4/3 pi r cubed. All right. So what they are telling us is that the volume is increasing at a rate. So again, if you see rate, you want to think derivative. So dv dt, the rate of change of volume with respect to time, is 100. All right, so we have that. And they want to know how fast the radius is increasing. So again, that's also going to be a rate, dr dt. And that is what we're looking for. We want to find the rate of change of the radius with respect to time, precisely at the moment when the volume is changing at 100 cubic centimeters per second. That's constant, but we want to look at it when the radius, we want to see how fast the radius is increasing when the diameter, all right? So let's get, because that's another thing we know then. We know the diameter at this particular point in time, and the diameter goes all the way across, right through the middle of the balloon. We know that that's this piece right here, that's 50, all right, but the relationship between the diameter and the radius is half. So this part right here, that's 25, and that's my R, okay? All right, so we've drawn a picture. We've labeled it in terms of my radius is R, my volume is V. I've got some equation here that relates everything, and I have my knowns. My known is that the radius is 25 centimeters. The rate of change of volume with respect to time is 100 cubic centimeters per second. This is what I'm looking for. All right. So now I come back to this equation here that relates everything, and we could probably add that if we haven't. If you think about it, we need to just add this here. We need an equation. All right. We just need an equation that relates the knowns with the unknowns, or the things that we need to find. So we don't have a dRdt yet, so the way to get that is take the derivative of both sides of this equation with respect to time. Okay, I want to take that and this, but the derivative with respect to t of v, or volume, that's just my dv dt. So again, let's not put any numbers in yet. We want to take the derivative of everything, and then we'll put the numbers in. Otherwise, if you put the numbers in first and then start taking the derivative, everything's going to be 0, and it's going to give you no information. All right, so here, 4/3 pi is a constant. So really I'm taking the derivative. We can kind of take that out in front, right? 4/3 pi. The derivative of r cubed, that's going to be 3r squared, and then we're going to multiply by dr dt. Just as we did in this first one, we took the derivative of x, we had 2x dx dt. Derivative of y, we got 2y dy dt. So taking the derivative of r cubed with respect to time is going to give me 3r squared dr dt. Again, you can think of this as the inside function in the chain rule. All right, so if I multiply this out, so I get dv dt equals, and then 3, this cancels with that 3, and I'm just left with 4 pi r squared dr dt. All right, now I know this. This is the point at which I can plug in, right? So I know that is 100. This is, so rewrite the 4 pi. R squared, well, r is 25, so that's 25 squared. Okay, dr dt. So now I just need to solve for dr dt in this problem. All right, so we can rearrange things here. So for example, if we take dr dt, and I'm gonna bring this over to the left side, divide everything by this. I'm going to end up with what, 100 over 2500 pi. All right, you can trust me on that. You can work it out, work out the details here. But ultimately, that reduces to 1 over 25 pi, which is approximately 0.0127, and our units are going to be centimeters per second, because you can see up here volume was in terms of cubic centimeters per second. So the radius, which is just one dimension, that's going to be in terms of centimeters per second. Okay, so that's that one. All right, now let's take a look at a third one. I'll just move this for the time being. All right, so we have that car A is traveling west at 50 miles an hour. Car B is traveling north at 60 miles an hour. Both are headed for the intersection of two roads. At what rate are the cars approaching each other when car A is 0.3 miles from the intersection and car B is 0.4 miles from the intersection? So again, we come back to this idea. I want to draw a picture and label it. Let's start with that. All right, so I've got car A, and it's heading west. I have over here car B, and it's heading north. Okay, so just like we did in the first problem, I'm going to label this X, and I want to label this Y. All right. let's now look at what else we know here. So we know that this 50 miles an hour, so that's going to be dx dt, right? Because this is he's moving west. In other words, this distance is changing at 50 miles an hour. So dx dt equals 50. Likewise, car B is moving north at dy dt at 60 miles an hour. Some other things that we know. We know that this is precisely at the point when car A is 0.3 miles, so this distance, x equals 0.3, and then y equals 0.4. Now, an important part, so what we've done again here is we've drawn the picture, we labeled it in terms of x and y, we identified our knowns. What do we need to find here? When we talk about the rate at which the cars are approaching each other, we're talking about the distance between the two cars. So if we look at this as the distance between the two cars, just because the next letter in the alphabet after x and y is z, I'm just going to label that distance z. All right, you can label it whatever you want, but ultimately we want to look at how that distance is changing with respect to time. In other words, what's the rate at which they're approaching each other. So what I need to find is dz dt. I want to find the rate at which they're approaching each other. All right, and hopefully it makes sense that even though this one's moving 50 miles an hour and this one's moving 60 miles an hour, that distance between them is closing even faster because it's kind of taking both of them into account. It's taking part of it's this horizontal motion, part of it's this vertical motion. All right, so how can we relate all of these? Well, again, we're going to assume that these roads intersect at a right angle. All right, and we can use the Pythagorean theorem again. So I'm going to have x squared plus y squared equals z squared. All right, again, these things are all changing. X, y, and z are all changing, so I want to keep them as variables initially. We know dx dt, we know dy dt, and we want dz dt. So let's take the derivative of each of these with respect to time. So I'm going to have, so if we take the derivative, I'm just going to kind of say the whole thing, what I mean by that is we'll take the derivative of each of them with respect to time. So I'm going to end up with 2x dx dt plus 2y dy dt equals 2z dz dt. And notice how this changes, how this is different from the first one that we did with the ladder. In this case, when we took the derivative, we got 0 because the length of the ladder was constant. It was not changing, so the rate of change was 0. In this case, we're looking at a distance that is changing. As these cars come together, this distance is changing, and that's where, and it's a good thing because ultimately this is what we're after. So what we need to do is try to fill in everything else that we know. So we know that x is 0.3, so I've got 2 times 0.3, dx dt is 50, plus 2 times y, which is 0.4, times dy dt, which we said was 60, equals 2z, which we don't know, but we can find it, dz dt, which we don't know, and that's the whole point of this problem, is to figure that out. All right, moving this over a little, let's find z, because that's the last piece. Once we know z, we can solve for dz dt. So we know that y is 0.4 and x is 0.3, so using this equation we can solve for z. So x is we have 0.3 squared plus 0.4 squared equals z squared. So z equals the square root of 0.3 squared plus 0.4 squared, and that equals 0.5. All right, so now let's just plug everything in. Let's put this in here and then crunch some numbers. So I'm going to have this is 2 times 50, which is 100 times 0.3, so that should give me 30. This is going to be 0.8 times 60, which should be 48. And over here, 2 times 0.5, that's just 1 dz dt. All right, so it looks like we have it now. dz dt equals 78. 78, and our units are going to be miles per hour just like they were. So again, this kind of follows our intuition that this distance is closing down faster than the horizontal or the vertical distance, because both of those come into account as we look at how this distance changes with respect to